Okay, so hello everyone. Welcome to today's live session. Today we are going to solve today's Leetcode problem, and those who are new to this channel, here we solve daily Leetcode problems daily, and it is a step-by-step unseen problem solving where I'm seeing this problem for the first time and I'll be solving it step by step. It might be the case that I cannot reach to the solution, but I'll try my best to get the entire problem solving right in front of you. Okay, so without any further ado, I'll say about three steps which we are going to do. First is reading the problem statement, understanding the problem statement, and the second step is to making an algorithm approach out of this. So in that, what we will do is basically we will build an algorithm which is a method how we can reach to the solution, and then we take constraints into the consideration and we optimize our algorithm, right? So this is algorithm step, which is step number 2. Step number 3 is actually getting into this code editor here and coding the entire logic which we have come up with. So that should also be thought beforehand, like before writing the code you should have idea about what functions and what data structures you are going to need. Okay, so without any further ado, I'll just check if we are live and then we can go ahead with the next one. Right, so we are live here and what data structures you are going to need. Okay, so without any further ado, right, so next what we need here is basically we will be jumping to the iPad screen and we will start our problem solving right away. Okay, perfect. I hope this is fine. Yeah. All right, guys. So now the question says construct binary tree from pre-order and post-order traversal. And those who don't know about pre-order and post-order traversal, I'll quickly tell about that. I know it because I remember it with a trick. So pre means this traversal is a method how we traverse in a tree. The way we write the nodes of the tree, the way we print the values of the tree. There can be multiple orders. The way we dig deep in the recursion tree, there can be multiple such ways. But based on that, there are these terms. So you have to remember that these terms apply to root node only. So if it is pre, it means you just write root in front of left and right. If it is post, you write root after left and right. What does that mean? For pre-order traversal, if you're doing a pre-order traversal, in that case, what we will be doing is we will be, since pre means we have to take the root into consideration, so we will print this value. Let's say this is 1, so we print 1 and then we go to the left subtree. This is the left subtree, and after getting done with this, we go to the right subtree. So we will be doing left subtree inside here. This is the root node, you just print it. Let's say it is 2, so we print 2 here. Likewise, then we go to the left subtree, we print 4 here, and then there is no right, so we are done with this particular tree. Then we come to the right of this tree where we print the 5 here, and then we are done with this whole tree. Then we come to this part of tree which is like 3, 6 and 7. So this is the way we write pre-order traversal, and similarly we can write post-order traversal where we first traverse left segment, then right segment, then we note down the root. Okay, so construct binary tree from pre-order and post-order traversal. It means that we will be given pre-order traversal and we will be given post-order traversal. Okay. And we have to create a binary tree out of it. Just a sec. Yeah, we have to create a binary tree out of it. Cool. All right. So we have to create a binary tree where we have to return. So given two integer arrays, pre-order is an integer array. is an integer array. Post order is also an integer array, where preorder is preorder traversal and of distinct values. Note this thing: the tree has distinct values, and post order is the post order traversal of the same tree. Reconstruct and then return the binary tree. If there is just multiple answers, you can return any of them, right? So we have these traversals given to us, and we have to return the binary tree which was actually there. There could be multiple answers, so we can return any of these. So what do we mean by a binary tree? Binary tree is a tree which can have maximum, where each node can have maximum two nodes, two children nodes, right? That's a binary tree. Right, so the main thing is to, like when we're talking about pre-order traversal, here you see one was there, here we see this was there. So it is quite evident, like 1 2 4, here we, the way we note it down, 1 2 3 4, 1 to 4, then we have 5 3 6 7. Luckily it was the same example which was here. Okay, so in order to construct this kind of tree, so first thing first, we are sure that this one is the root node if we have the pre-order traversal. Make sense? Right, so we are given the root node with us. Now from the pre-order traversal, I can say that this 2, the next element which is here, let me erase it a bit. So the first element is the root. The next element, now there can be possibilities here. What possibilities? The possibility number 1, this next element which is 2 here, it might be the case that one has left child, right? It might be the case it has no left child, it has just right child. Either of these, right? Either of these is possible. That is why we are getting this value. So now how we will get to know that 2 is the left node or right node? So regardless of where is 2 in this tree or not, we can be sure at this position that whatever next node we get, it can be the left one, it can be the right one. Both of these cases are possible. Correct? Both of these cases are possible at this moment. Now, there can also be a case where we can have 1, 2, and 3, right? There can be also a case where we can have 1, 3, 2. I'm not sure about this 3, I have just written it. It could be any node. So now, the thing is, pre-order traversal is giving me surety of this one, but it cannot give like where exactly the second node lies. All of these positions are valid. All of these are valid. Let me think. This one is not valid because in this case we need to first print 3 then 2. So this is not valid. Since we are printing 2, this can be the valid ones. These are the valid ones. There are 3 steps here. Now what can we take out of the post order traversal? The post order traversal says that left, right, then root. So we traverse the left end and then we traverse the right end and then we come to the root node. So it means that we will just, in the post order traversal, we will be done with this part. So here we will be first writing 4 here, then we will be doing with right part which is 5, and then we write the second node here. So this particular node, before this all the values are its children, right? So the node which we see here is the leaf node, right? Now, so the moment where we see 1 in this node, it should be the end, right? So let's say the pre-order traversal is like this: 1 2 4 5 3 6 7. This one has to lie at the end for the post-order traversal because it is a root node, correct? And left subtree and right subtree are 4 5 2 6 7 3 1. left subtree and right subtree. So the first thing first, which starts from here, is the left, then we have right, and then we have the root node. But there can be cases when there is no left, then there is no right. Right. But we can surely say that before this point, whatever we see here are children of 1. Make sense? Makes sense to me, yeah, it makes sense to me. For 2, if I connect this with this particular thing here, for 2 I can surely say that this whole thing are the 2 children, right? For 4, we can see 4's children are before this, so there is no children of 4. For 5, again you have to be careful here. 5 is a right subtree, right? How to get out of this situation, man? How to build a logic which is robust and it works. Obviously, we have to use both of these arrays in order to get to an answer which is good, right? Which is a good answer. So now we need to really think a way out by using these two. First, we found out this, that all of these are children of 1, right? And this guy itself, and whatever we see beyond this, has a possibility of being a children, right? It is obviously children of 1 only. So we know that this 2 is a children, right? So we are good about 1. We know that this 2 is a children, right? So we find its presence here. So what we see that if this node had if this node had any of the children, it will appear before before that in this region. It could be like till here, or anything else. Or it is also possible that this 2 has no children, right? So we are sure about this. So we know that 2 is there. It means that 2 is somewhere, right? Now we don't know about the exact position of 2, but if we know that there is a right subtree, 2 should be surely at the left, right? So we have 2 here. So next we come to the 4 one. Now if 4 lies besides 2, so we find 4 to be here. What does that say? Is that this is basically whatever we see beyond this has the possibility of being a children of 2. Why? Because it lies in this region of the post-order traversal. So we know that this is children of 2. Guys, I think this is a very simple way they solve it using if I go to the basic fundamentals of a preorder traversal, it means that it is written the way we traverse like this. So we started from here, we took the first element over there. Now we can have gone to this part and this part. Let's say we go for this part. So we have, here we have 2 and then we have 4. Then when to stop? That's the problem, right? When to stop? And that is exactly where this post-order traversal matters, because in post-order traversal, what we do is basically this. We go all the way up to post, since it is a post-order traversal. So we go all the way up to here. Here we mark the first one. So this will be the second one. This is the third one, right? So here we keep going in this direction. And here also we reach the leaf node, right? Some point of time we reach the leaf node. And here we start with this leaf node only. So we know that this 4 is a leaf node, right? It is a leaf node for sure. It is leaf node, and that too, it is that kind of leaf node which is, let me show you. It is that kind of leaf node. This is the starting point of the post-order traversal, right? And this is the in the pre-order traversal. Let's say these are 1, 2. These are 1, 2, and 3, right? This is 4, 5, 6. In the pre-order traversal, we will write something like 1, 2, 3, right? And then we write 4. This was root, left, and then right. Then we write 4, 5, 6. In the post-order traversal, we will write 4 because it is where we end. And then we go in this particular tree, we write 5. And here we write 6 as well. Then we write 4, and then we write 2, and then we write this particular subtree where we write 8, 9, and 7. Right, this is the approach. So what we see here is that the starting nodes are actually the, so this 4 is here. It means that if we connect these two nodes, it means that these are the leftmost boundaries of the tree. So if I just erase this, from this I can analyze that these are the leftmost boundaries of the tree. Like this, we can surely say that it can be left or it can be right. Are you sure? If they are at right, like this, 1, 2, 3, 4, then pre-order traversal will be 1, 2, 3, 4, same. Post-order traversal will be left, right, root. So it will be like, this will be like 4, 3, 2. Yeah, yeah, these two cases are possible. Both of these are possible. At this point of time, both of them are possible, right? So this is there. Now let's come about the another one. You notice here, this is 5. Now 5 is matching till here, right? So what does that mean? We are sure about this because that is the case, right? Now we know that this 5 is again a leaf node, because if it had more children, then they would have come before this, right? It is a leaf node. So now what we say here is that we're done with this tree and then we are having this tree as well. For this 4, what can we say is, I mean this 5 is there, 5 is matched with this 5. What does it physically mean? Like here we know that this is the end of that part, end of this era. Now we go to the right segment of this particular node, which is, to be honest, which is, yeah, there is a possibility that this does not exist, and it can exist from here, it can exist from here, it can exist from here, here. 3 places. Now if there was a branch here, on here, if there was a branch here, it means that left, right. This is really tough, man. Until and unless you already know how to solve these problems, it is very hard to build these approaches. But I will try. I'm not a coward or something that gets overwhelmed with this. There can be multiple trees, right? So we should do actions which take us in a good direction, which is not a wrong direction. Right, so what we see here in post order traversal, this means that 5 is the, if 5 is printed, it is the, at the moment it is the root node which has no children. Right, if it had children, so if 5 is like that, now 5 can come here. Since it has no children, we can be putting 5 here, here and here, anywhere. That's fine. These are the 3 locations of 5. Now let's come to the 6. 6 is right beside it. Means now 5 have no children afterwards. No children afterwards. Then we have this 6, right? And we should know that 6 should exist in the right subtree only. One, two, three. Actually, I'll take a fresh example. My mind is getting blank at this. So let's see, we have this 1. Right, this is a binary tree. Okay. If I write the pre-order traversal, it will be 1, 2, 4. Then we have 5, 6, 7. And then we have 3, 8, 9, 10. Post order traversal, it would be like 4, 6, 7, 5. Then we write 2 here. Then we write 8 here. Then we write 10 here. Then we write 9. Then we write 3. Then we write 1. Okay, so here we see this. This is the first element, which means it is a leftmost node. So we can say that we have a configuration like this, or we can say we can have a configuration like this. From this speculation, both of these are possible. For 5, if we check here, before 5 there are 2 elements, which is 6 and 7. What does that mean in post-order traversal? That simply means that 1, 2, 4 is there. Now then there is 5, right? So we are sure that 5 is a branch now. So this is a branching. We have to start branching from this part. Sure, we have to start branching. Now where is that branch starting? It could be here, it could be here, it could be here. Now we see that it has two children. It could start anywhere, by the way. The thing that it starts here, not here or here, is that uh, that thing is there. Or if we have 5, 6, 7 in this scenario, if we have more nodes here, that will simply go in this way. 5. Here in this case, it should be like, this is not possible if there are more children, because if there were more children, it could start from either here, then in that case, that would be the answer. Or it would start in a branching, but in that case of branching, it is possible that we can do it this way. 1, 2, 4. This will also print the same thing instead of that. It can be the leftmost node in these ways possible. 4 के बाद we have things like this. But in that case we won't get this 2 na. So we get this 2, 1, 2, 4 we get. In the Postorder traversal is still at 4. Then we have to get 5, which has 2 children, 6 and 7. 4, 6, 7, 5, 2. So this is basically this case only. This is only that case only, but not that case only. It's a different case, man. So this is another possibility. For if we are focusing on this particular possibility, then we can sure shot say that 5, 6, 7 is there. So we can sure shot say this thing is that we can put this guy right here, 5 with a 6 and a 7, correct? Let's move to the 6th one. 5, 6, 7. 5, 6, 7 makes sense to me because 6, 7 is here as well. So I just worry about this 5. Then we have 6, 7 beforehand, which means that they're children of 5. So since they're children of 5, they must be there only 6, 7. So we find that how far is 6 from 7? And we have 3, 8. 3 is here. It means all these guys are children of 3. Really? I don't think so. But if I notice one thing, let me just write this again, then I can notice something here. 1, 2, 4, 5, 6, 7, 3, 8, 9, 10, 4, 6, 7, 5, 2, 8, 10, 9, 3, 1. 1 is here, these are the children of 1. 2 is here, these are the children of 2 for sure. 4 is here, these are the children of 4. 5 is here, these are the children of 5. No, they are not. For 5, we get this 6, 7. For 6, we get only this. 7, we get this. For 3, we get only this. without 2, right? I still cannot get it, man. I still cannot get it. Cannot get it at all. So this means 1. This is the family of 1, I'm sure about this. Now for 2, and then we notice all the whole bunch of things before 2. This is the family of 2 for sure. There is no guarantee that that guy could be there. Why? This is painful, man. Very much painful. But I want to break it down. I want to understand pre and post order traversal from heart. Okay, let's take steps in that way only. Let me erase this thing because it has no conclusion. So what does a pre-order traversal means? If I go step by step, this means that 1 is the root node. For sure 1 is the root node. Fine, I place 1 here. Now, what can we interpret from the post order traversal about 1? It says that 1 is the root, it will exist at the end. All of these are the children of 1, right? Right, so now I'm trying to do divide and conquer thing. So I'll divide this problem. We don't know the solution, but we divide the problem into simpler step to such a step where we know the solution. That's the funda. So this is the 1. We know that this is the children of 1. And we also know that all of this is children of 1. Now we have the problem which has shrinked to this part. Right. So whatever we see at the second spot is actually, it can be like left subtree, right subtree, and the root node. So it could be left and so now let's say 1 has some children here. If that is the case, in this case, this 3 is literally that we have traversed the, this can be like the right subtree, right subtree's head, right? So we can have another problem statement where 3 is the 3 is the root node, right? This says that 3 is the root node, yeah, and this says 2 is the root node, right? So what can we say here in this case is that we have one node, so now we see that this and this are different. It means that there are two nodes at this level. First is 2, another is 3. For 2, the problem space is this much area, right? And for 3, the children space is children space is this area, and here it is this area, right? And here for 2 it is like this area. Now this has actually divided, this has divided, and I have actually found a way how we apply divide and conquer to these algorithms. Basically divide and conquer, I got the gist of divide and conquer. which is that you cannot solve the problem, which is very much weird at the first place, but we keep dividing it into smaller sub problems so that we solve it, right? So it makes sense in this case here. Now, I'll tell you how we are going to actually solve this. I think the algorithm is under my control now. So we have this sections here. So we check the next guy here and we check the next guy here, right? If you're talking about this node, the right of the this particular segment and the left of the this particular segment are the same. If they're same, then there is only one possibility, and that is the either left possibility or either right possibility. So we'll go with the left possibility. But if they are different, it means that there are two flag bearers, two sons of this, son or daughters or whatever, everything. Two children are there of one. Now, for them, the problem space is really constricted. What is the constricted problem space? So for 2, we have this case here 2, 4, 5, 6, 7, and 4, 6, 7, 5, 2. So this is the root. Now we do the same thing. We see that these two things are different. So from here we need two nodes. One is the 4, one is the 5. And for 4, we find its position here. For 4, the space is actually this. For 5, for 4, the space is actually this. For 5, the space is this. Right, so for 5 we get for 4 we get here no space here. For 5 we get this space here. For 4 we got no traversal next. For 5 we got 6, 7, and for it is actually 5, 6, 7 and 6, 7, 5. So you see, now you check again, do the same thing, right? So the problem statement gets reduced, right? I think I have got the idea. Now I'll explain it uh, in a good way now, because it required a lot of efforts from my side to figure it out myself without taking any hint that what kind of algorithm we need to apply, right? This is a really, I won't say non-intuitive if you know divide and conquer, but it is really a hard thing to come up with, right? It's not that obvious unless you have practiced similar problems before. So guys, this is the case here. Now, now I'll talk about the exact algorithm. Okay, so the algorithm says, I'll take an example here, the same one. 1 2 1 2 4 5 6 7 8 9 10 7 5 2 8 10 9 3 1. So what we have to do, so we have to, first thing first, we have to consider this range. I'll call this range from L to R. This is also here, I'll call this L dash to R dash, right? So what we're going to do, obviously these two values will match, right? Now what we need? So we need to find the position of this 2 in this one, which is here. I'll call this x. Position x dash, the position of this 3 in this one, which is x here, right? Right. And this I'll call L minus, this I called L R minus. Now, if there was only 2, in that case, yeah, there are two possibilities that if L minus is equal to R minus, which means that this is a case of one children, one child. So we can go with like either left or R, both of them are possible. Now, if we come to the else statement, it means there are two children. So L minus to from L minus to x minus 1, this is x minus 1 here. This is the pre-order traversal, and then we have the post-order traversal, which will be L dash to x dash. Got it? This is for the first children. For the second children, which is basically this 3 part, what we need here is basically x dash plus 1. The post order is x dash plus 1 to r minus minus 1, right? Till here, and then from here till here, basically no minus 1 is needed here, right? And from here it will be simply x till r. This way we assign L minus to the left part, and here in this case L minus, and here in this right case it is R minus, and for these nodes we do the computation. So this is as simple as that, but what we need to do here is to basically find this positions x and, right, we find the positions x and x dash. R is known to us, x dash we need to find. We need to find x and x dashes. Makes sense? And then we divide it, and at the end we conquer it, right? I'm feeling very happy because we have come to a conclusion. I was so blank in this problem that you won't even know like how I was feeling. Okay, I was thinking to quit, but suddenly I thought like I should dig deep and deep, and we came up with that. Now let's go ahead and plan our code approach. So now let's go ahead and check the constraints, if the constraints support it or not. Because what we are essentially doing here, this is the step one for like for L2R it is, right? And then we keep breaking it down into segments, and those segments are kinda unique. So this is going up to order of n square. If we look up for these values, it is definitely order of n square. If we look where is x dash, it is order of n square. But if we see, okay, so the length is really short, so we can afford that. 30 square is nothing, right? Pre-order values are less than, okay, the node values are also like below 30. All the values are unique. Post order length same. Pre-order post order is also same. It is guaranteed that they are of the same binary tree. Yeah, that's fine. So here we can really go with order n square approach, but I would like to have a map, pre-map, post-map. From values we get the indices, right? Like a map which stores, let me use some other color. We have a pre-map which stores value and index, and we have post-map which stores value and its index. Make sense? I think we are done with the code at this very moment because we've already decided our data structures, right? Now we have to define our recursion function. That is pending, yes, that is pending. So this is the third step. So we need, these are the data structures. We need pre-map, we need post-map, and we need a recursive function which has the parent node, which has the pre-index px, or let's call it pi and pj. I should call it pr, but since pre and post are like similar, they start with p only. So I'll do it r and o, pre ka r and post ka o. So I'll call it ri, rj, and oi, oj. Correct? These are the basically the segments where we have the similar problem broken down, right? And then we have the obviously the traversal arrays. This is pre-array, this is post array. That's all we need. Also these maps are like there. This is the recursive approach. Where do we stop? We stop when these ranges are invalid. If this is invalid, it means Ri is less than Rj, or Oi is greater than Oj. This is also greater relation. Then we have to just return. Otherwise, we have to compute these x and x dash, and we have to apply these two logics, right? So this is the thing, this is the function which will do all the things. Now let's move to the coding section. Since it was a medium part problem because I was not aware of the things which I could have done in these cases. Now I'll move to the coding section and code it up. The coding it is very very important. You might be sure with the approach, but when it comes to code, until and unless you code the problem, it is not solved. Right. I think it will go up to 3 o'clock. Let's see. Okay, so what are the data structures which I need? And I want to make it smaller. This should be PR, this should be PO. So first thing first, we have the data structure which is a map, and I call it pre-map, PM, a preem, and prem, right? And prio. Pre-map, sorry, post order, right? Pos and prem or pos, posh and pom, prem and sorry, this should be like POSM is great. Pre-m and pos-m, right? Post-m. Post is a bit. Pre-m and post-m. Alright, so we have this map here. Let's create this map. I'll create a n. Right, then we have this thing here. First thing first, what we need to do is to construct these maps, right? So we do this frame of pri is equal to I, postem of poi is equal to I. I think this is good. Now we have to construct that recursive thumb function. So here I'll just create a parent node, or we will create it later. I think it's better to create it right here. Yeah. So I'll call this auto root is equals to new tree node, and the value will be pr0. Now we have to return this as well as an answer, and then we need to do this thing. We have a recursive function, which is a divide and conquer function, and here we need quite some variables. First we need the root node, which is a parent node, and then we need ri. Ri is here in this case, ri is the boundaries, so it is 0 till n minus 1 to be precise, because we are talking about indices. Then we have oi and oj, so this will be also same at this point. And then we pass the things which we have created, which is the first thing is prior, po, and frame and postem. Right. Here we define the function in a fully fledged manner. It is a void function which takes the tree node parameter, which I call is that node, and then we have integer ri, integer rj, integer oy, integer oj, and then we have the things passed as value, these two values. And then we have this map of int comma int, and we have prime here, map of, we have postem. Yeah, here we have to pass all of these by values in order to avoid a copying and increasing our recursion stack size. This is fine. Alright, now what do we need next is to write our logic. Okay, if we see that ri is less than rj, or oi, again it should be greater, is greater than oj, in this case we will just simply return this is our base case. Now we have to find x and extras, right? Okay, so there's one more problem here, which is we will be accessing an index. Now we have to focus on the algorithm, so I'll show you. So we will be accessing the index which is next to this, right, and which is next to this as well, previous to this, right? So the length of this particular thing should be at least 2, right? That is a validity check. So this is not sufficient. The difference, basically, obviously ri should be lesser, rj minus ri, this difference should be like, if it is 0 and 1, there are zeros and ones, it should be 1. The difference should be at least 1, right? Is greater than equal to 1. is not, is in that other case it would be like less than 1. Oj minus oi is less than 1, right? This is the case here. Then only we can have like this kind of uh, movement. Basically we can access this index, we can access this index. So first thing first, we have to calculate L minus and R minus. So we are calling this, actually we are calling this, let me just overwrite this. We are calling this, here we are calling this Ri, this is Rj, this is Oi, this is Oj. So this is actually Ri minus, this is actually uh, Oj minus, right? So I will call it like this here. Let me show you. I'll create two variables. First is underscore Ri, which is Ri minus. Ri minus is Ri minus 1. And then we have Oj, which is, so this is actually plus next index. This is actually a previous index. Okay, Oj will be anyway greater. Correct, right? We got these two indices calculated to us. We already know that what is, uh, yeah, we already know what is integer Rj is basically the same Rj here. Integer underscore Oi is actually same Oi here. Now we need to have x, which is, so what is x here? It is the index of this particular number, Oj minus number. So in the pre-order traversal, pre-map, the post order index, we take this Oj minus, we get this x, and then we get this y, sorry, x dash, which I call it like underscore x dash. This is in the post order, so post map, this is like PO, a pre-order traversals, and this is the next one, which is underscore RI. Now there is a check, there are two checks here. First is the check for one child only. Actually this way, only one child. Right? How do we check that? We check with this L minus, L minus, which means Ri minus is equal to, if that is equal to this one, Oj minus. Ri minus and Oj minus are equal, then one child. If Ri minus, which is underscore Ri, basically the values, not the indices. So it is PR pre-orders, this is equal to post orders Oj. In that case, what we need to do is to new auto n equals to root our new tree node. The value will be simply PR of any one of these. PO. No, this is PR only, right? So we created this. And in the next step, what we will do is basically make it the left one of that tree. Left child. So how can we make it a left child? We can have something like this. Nodes left equals to n. Now we do this recursion of n Ri. Now for this Ri would be right. So in this case, what could be the Ri? So this is a case where this part, this entire part, yeah. So let me just tell you that case. So that case is like this here. Um, yeah. So these two have matched, right? So we need to take from here till all the way up to here, from here all the way up to here. So this is actually Rj. This is your Ri minus. This is your Oj minus, and this is your Oi. So for simplicity, we can use these values only. Since we are not splitting here anything, so I can just use Ri underscore Rj underscore Oi and underscore Oj. And then we have pre, then we have post, then we have frame, and then we have post them, right? Else we are sure to have two children, auto n1, which will be new tree node, it will be created from this one, and we have auto n2, which will be our new tree node, which is created from pr of underscore oj, right? And then we make them children. So roots left is equals to n1, root right is equal to n2, right? This is the case here, and what we need to do next is basically pass the recursive function, recursion 1, recursion 2. That is it. So now what should be passing here is this is for n1 here. For n1, now let me think. This is basically this approach only, right? So I will show you how we can do this. So it's like this is your underscore ri, this is your underscore rj. Somewhere there is x dash which is matching with this guy. So this is your, and here it is your underscore oi, and here it is your underscore oj, and there's one big guy here, one big guy here, right? So what we'll do here, so for this part we need to go from here till this is x index x minus 1, and in this one we will go from oi till x dash. Exactly, x dash will be included here. It will be included, right? It will be. So this is underscore ri x minus 1 underscore y till x, and for the next part this guy it will be like x till underscore rj and x plus 1 till underscore oj. So we have to do this first, underscore r I to x minus 1 underscore ri till x minus 1, right? And from their end we will have underscore y till oj minus 1. Sorry, x dash minus 1. X dash minus 1. PRPO frame Boston. Here we have been passing n2, and this will go from x till underscore rj, right? And then we go from in the downside x dash plus 1 till all the way up to oj underscore oj. This should be actually from x till rj, right? I have not done this otherwise. Why is there two computation and here is only one? From x till rj, correct? From x plus 1, that's true. From x dash plus 1 till oj. Yeah, x dash plus 1 is required until there. But I'm doing it for this, right? So for this guy, it should be like this only, right? Correct. Correct, yeah. Yeah, so I think this is the entire code. And if we make any mistake, we'll be literally debugging it till 3:30, and it is so use. There is no root. Let me just change it to node. Great, so we are getting some correct answer. Basically, we are getting wrong answers only. Okay, now it's a big debugging thing here. Where exactly is the error? That is a big thing. So what we get output is this. The expected output is this. 4, 5, 6, 7. Is the difference? There are a lot of hiccups happening here. For one, let me go by step. For one, it is like we got two children, right? So we should just comment things, right? Okay, so if we comment stuff, my debugging skills are not that good, but I will try to improve it, right? So for only one child, you will write something like this. One child here, given handle, you just print all those values. Underscore array, underscore rj, this is your y, this is your oj. So how we're starting it actually? We're starting with from 0 to n minus 1, and we have created a node at this place. This is the 0th node which is already created, which has some value, right? Now what we have done next is we have moved to the next one, next node, and we have moved to the previous node in the post order one. Now we have checked that Ri Yeah, if the values are same, it means there's only one child. In that case, we do this thing that we assign it as the left child, and then for the left child, for the very left child, we will pass it that way. Correct. It seems correct to me. Let's see what happens here. Okay, so for the first thing first, it has treated it as 1. RIRJ is a different stuff. How is RI and OJ are same? So first thing first, they had created the sizes, which is period size. We passed 0 and this is like 7 minus 1 6 0 to 6, right? We passed 0 6 here. Yeah, I need to check RI and OJ. RI and underscore RI and OJ. So underscore RI is 2, underscore OJ is 0. How is that even possible? This should be like we have passed actually we have passed 0 over here and 6 over here. Underscore I should be 1, right? Right. How are these things calculated, boy? First thing first, we are passing it like this only, right? We are passing it as n minus 1, right? Let me print these same values here without the underscores, the original values which we get. Maybe we can write it at the top. Okay, let's run it. Okay, so I have not added a comment over here. My bad. This is for 2. Okay. Correct. So this was the initial pass. Here we got 1 to 6. What is this? 0, 1, 1 to 6 and 0 to 5. 1 to 6 and 0 to 5. 0 to 5. Correct. We got correct thing. So we got two values over there. Right. So we pushed 2 and 3's, right? So but we can see here that it is not pushed correctly. 3 should be the right of it. 3 should be right of it. So underscore OJ was underscore OJ was underscore OJ was 5, which is this index. Okay, so my bad. You can see clearly my bad here. This should be PO, right? Still, it is not that correct. We have to debug it. For some values, it has taken null. Okay. For 5, it has taken null, right? I think the problem is here. When we pass the children, in the end, what is 5? In this case, 5 is like, in this case, 5 was like, oh, sorry. Yeah, in this case, 5 was like here. Give me a second, guys. I can debug it. Basically, we have to do this. Some sort of things have to be optimized, right? I think it is getting null valued because we actually passed some ranges. Like the index of 5 is for 5. If you see, 5 is a children of 2, right? So it will be tackled when we were tackling 2, right? So actually the index was, first of all, okay, this was the case here. And this is where we went from here and here. So 1 say 3 tak. This is the idle index, and 0 say 1. 0 say 1. 0 1. So it was 1 3 and 0 1. 1 3 is good, like 2 4 5 is good. But here it should be like 4 5 and 2, like 0 to 2, not 0 to 1. So in this case what happened was this, that the let me see here, this was good, this was good, it was well captured. Underscore oi and x minus 1. Underscore oi is actually the starting point, which is correct. 0 was correct here, but the next thing which we took here was underscore x minus 1. Underscore x minus 1. Underscore x minus 1 nahi, it should be underscore x itself, because that's where we match. Guys, I'm 100% sure now it will be, the error will be gone. See, this is the confidence, man, because there are very less chances of errors when we go this way, right? Because everything is under control. Okay, yeah, I'm sure about this. If it fails, then that's surely my blunder mistake, and I should really feel regret on that. I'll do a submission, and I'll do a test submission, and then I'll do a final submission, and I'm saying it should be 100% correct. This is a bold decision which I am taking, and let's see if we are at the right place with right time complexity and no missed test cases. So guys, this is how we divide and conquer. Yeah, maza aa gaya. So guys, this was really fun, really stressful, but I enjoyed it. Enjoyed every bit of it, and now we have solved it. You see, I'm not sure how many people are watching, but we started 78 minutes ago. We have solved this problem in. So guys, this was really fun, really stressful, but I enjoyed it. Enjoyed. Okay, so this was great. I think it took around 1 hour 18 minutes, which is good for good medium problem. And look at the solution, man. This is 0 ms beats 100% of the complexity, right? Space wise, it's not that great because we are using maps. I understand that. Correct. Yeah, so guys, I'm really happy to solve this question. Now, the takeaway from this will be how pre-order and post-order traversal. This is a classical problem, to be honest. This is really a classical problem. It can be popped up in any interviews where we appear. I guess I have solved it previously, I'm not sure about that. Now, this is my first submission. And guys, this is it. Yeah, let's format the code. And there we go. Right, this is great. Okay guys, so this is all for today's video, today's session actually, and we will see you in the next one. Goodbye. Good night actually. Right. Okay, stop streaming.